Good afternoon, everybody. Let us start our today's class. Today we will read what is zeros of an analytic function. Okay. Zeros of an analytic function. So what do you mean by zeros of an analytic function? So first we will see its definition. So what is its definition? Let f of z be an analytic function. Let f of z be an analytic function. Let f of z be an analytic function defined in a region D. Defined in a region D. Let A belongs to this region D. Then A is said to be. Then A is said to be a zero of order R. This is a zero of order R for f of z if f of z can be written as z minus a to the power r into phi of z. So if I can write my f of z as z minus a to the power r into phi of z, where phi of z is analytic at a, phi of z is analytic at a, but phi of a is not equal to 0. Okay, so if you can write your f of z as z minus a to the power r into a function of z, where this function of z is analytic at a, but this function at a never be equal to 0. So if this condition is satisfying, then z minus a to the power r we are getting means z is equal to a is a 0 of order r. Okay, this is the definition. So now I'll see one or two problems. So let me first problem, example 1. Consider f of z. So if I will consider my f of z as sin z, so you know the series expansion of sin z. So you can write sin z as this is z minus z cube by 3 factorial plus z5 by 5 factorial minus z7 by 7 factorial plus dot dot dot. So if I will take z common here, I will get 1 minus this is z square by 3 factorial plus z to the power 4 by 5 factorial minus z to the power 6 by 7 factorial plus dot dot dot. So I can say this is z into a function of z, where the phi of z, this phi of z, which is this is 1 minus z square by 3 factorial plus z to the power 4 by 5 factorial minus z to the power 6 by 7 factorial plus dot dot dot, where phi of z is this one, which is analytic at z equal to 0, which is analytic at z equal to 0, and z of 0, this thing is not equal to 0. Z of 0 is a 1 and which is not equal to 0. So we can say that z is equal to 0 is a 0 of order 1. Okay, because this is z into phi of z. Z means I can write this one as z minus 0 into phi of z. Okay, so what is z minus that number? That is the 0 and its power is 1. So this is a 0 of order 1. So go to next page. Let us see another example. Problem 2. Let f of z, if I will take my f of z as z minus 2I whole square z plus 3 whole cube e to the power z. So if I will take this as my f of z, then you can say here z is equal to 2I and z equal to minus 3 are zeros of order 2 and 3 respectively. Okay. Similarly, if I will take another example, example 3, let my f of z is equal to, this is z square into sine z. So if I will expand this thing, this is z square whole into the expansion of sine z is z minus z cube by 3 factorial plus z 5 by 5 factorial minus z 7 by 7 factorial plus dot dot dot. So if you will take z common from this bracket, then in outside there will be z cube, then this is 1 minus z square by 3 factorial plus z4 by 5 factorial minus z6 by 7 factorial plus dot dot dot. So I can add this one as z cube into phi of z, where phi of z is this one, which is analytic, where phi of z, which is analytic at z equal to 0, and this phi of 0, phi of 0 will be 1, which is not equal to 0. So you can say, so z is equal to 0. This is z minus 0 to the power q. This one means this is z minus 0 to the power q into phi of z. So z equal to 0. Z equal to 0 means what is your z minus a. So z equal to 0 is a 0 of order 3. Okay. Similarly, if I will say another example, okay, let's go to the next definition. So next definition is your singularity. Now go to next page. So what do you mean by singularity in a analytic function? What is its definition of singularities? So a point A is said to be a singular point. A point A is said to be a singular point, is said to be a singular point or singularity. A point A is said to be a singular point or a singularity of a function f of z, if f of z is not analytic at A. If f of z is not analytic at A, this is the first condition, f of z should not be analytic at A, and f is analytic at some point, and f is analytic at some point, f is analytic at some point of every open disk, z minus a less than r. Okay, so what is the definition? A is said to be the singular point, A is said to be a singular point or a singularity of a function f of z if f of z is not analytic at A and f is analytic at some point of every open disk z minus a less than r. So if you take any open disk with its center A and radius r, then f is analytic at some point of its open disk, and f is not analytic at a. If these two conditions are satisfying, then you can say a is a singular point of f of z. Okay. So if we will see one or two example. So the example one, consider a function f of z. Consider a function f of z is equal to 1 by z. So if we will take its derivative, then it will be minus 1 by z square, and this thing does not exist, or this is 1 by z square if z is not equal to 0. So if z equal to 0, f of z does not exist, also your f dash z does not exist. So thus you can say f of z is analytic except at z equal to 0. f of z is analytic except z is equal to 0. Okay, so z equal to 0 is a singular point of f of z. So we can say z equal to 0 is a singular point of f of z. Similarly, if I will take another example, suppose my f of z is 1 divided by z whole into z minus I. Similarly, this is a function, whatever its first derivative may be. But the function is not defined at z equal to 0 and z equal to I. So you can say z equal to 0 and z equal to I are the singularities, or are the singular points of f of z. Okay. So now go to next page. The next I will give you the definition of isolated singularity. So what do I mean by isolated singularity? So what is its definition? A point A is called isolated singularity. A point A is called isolated singularity. A point A is called isolated singularity for f of z if it satisfies two conditions. The first condition is f of z is not analytic at z equal to a. First condition is f of z is not analytic at z equal to a. And what is the second condition? Second condition is there exists r greater than 0. There exists r greater than equal to 0 such that f of z is analytic, such that f of z is analytic on 0 less than z minus a less than 1. So this is the deleted neighborhood of a whose radius is r, and this is a open disk whose center is a and radius is r, but excluding the point a. So isolated singularity means it is not analytic at a but except at a. If you will take any uh, open disk around a, it will analytic at every point of that open disk. It is analytic, you can say this is analytic in this whole deleted neighborhood of A. That means you can say for this second point, that means the neighborhood z minus A modulus less than R contains no singularity of f of z. That means this thing contains no singularity of f of z except z is equal to A. Okay. So this is the definition of isolated singularity. So if we will see an example, so if my f of z is equal to z plus 1 whole divided by z square whole into z square plus 1. So if I will take this as my f of z, then it has three isolated singularities. This one has three isolated singularities. It has three isolated singularities. It has three isolated singularities. They are, uh, if you will take the denominator as 0, whatever with the numerator, if denominator will be 0, the function is not defined, so the denominator will be 0 for which value of z? Z equal to 0, z equal to I, and z equal to minus I. Since here the function is not defined, so how it will be analytic? So these are the points where the function is not analytic. Okay. Similarly, if I will give another example, like example 2, suppose my f of z will be 1 by sin z, and for which value of sin z, or for which value of z sin z will be 0. So if sin z equal to 0, then the function is not defined, so it will not be analytic there. So for which value of z sin z will be 0, so we can say the singular points are z is equal to 0, plus minus pi, plus minus 2 pi, plus minus 3 pi, like this. Or you can say this is plus minus n pi. And these are isolated singularity. And these are isolated singularities. These are isolated singularities. Now, if we will see what is the from the Lorenz series, Laurentz, you know the Lorenz series. So what is the Lorenz series says? If f of z is not analytic at A, then if f of z is not analytic at A, then f of z can be represented as a power series, or f of z can be represented as a positive and negative powers of z minus a, and that is your summation of n from 1 to infinity, that is bn divided by z minus a to the power n, plus summation of n from 0 to infinity, this is an whole into z minus a to the power n. And what is your a n bn, you know already, where a n is equal to, this is 1 by 2 pi I integration over c, this is f of j dj divided by z minus a to the power n plus 1. Similarly, your bn is 1 by 2 pi I integration over c, f of j dj whole divided by z minus a to the power minus n plus 1. And here in this first term, here the z minus a power is negative, because it is written as bn divided by z minus a to the power n. So if you will take this z minus a to the power n to numerator, then it will be bn whole into z minus a to the power minus a. So what is the negative power of z minus a? This thing is called as principal part or singular part of f of z. The negative powers of z minus a in the Lorenz series expansion is called, this is the principal part, this is the principal part or singular part of f of z. So whatever is your f of z, if f of z is not analytic at A, then by Lorenz series expansion, you will get its expansion in this way, and the negative powers of z minus a to the power n, these are called the principal part or the singular part of f of z. Okay. So now by considering this singular part of f of z, we can classify the singularity of a function into three types. So now go to next page. So here we can write the singular part of f of z or the principal part of f of z, the principal part or singular part of f of z at z equal to a determines the character of the singularity, determines the character of the singularity, determines the character of the singularity. And there are three types of singularity. There are three types of singularity. First one is a removable singularity. Removable singularity. And second one is your poles. And third one is your essential singularity. So by seeing this principal part or singular part of f object from the Lorenz series expansion, so there are three types of singularity. Okay. So the first singularity is your removable singularity, second one is your poles, and third one is your essential singularity. Now, if I will say the first one first, so what is the removable singularity? Removable singularity. So, what is the definition of removable singularity? Let A be an isolated singularity of f of z. Okay. Let A be let A be an isolated singularity. Let A be an isolated singularity of f of z. Then A is said to be removable. Then A is said to be then A is set to removable singularity. Then A is set to be removable singularity if the principal part of f of z, if the principal part of f of z, if the principal part of f of z has no terms, f of z at z is equal to a has no terms. Okay. So if I will see, suppose my f of z can be written as n from 0 to infinity a n z minus a to the power n. I can add this one as a naught plus a1 whole into z minus a plus a2 whole into z minus a whole square plus a3 whole into z minus a whole cube, like this. So here there is no principal part of this f of z because there is uh, there is no negative powers of z minus a. Here all powers are positive and here the power is 0. So there is no negative powers of f of z. So we can say here z equal to a is a removable singularity. So how the singularity can be removed? That means since a is a singular point, so at z equal to a the function is not defined. So if I will write a limit z goes to a, here f of z is equal to a naught, because if this is your f of z, so if I apply this limit z goes to a, so z minus a will be 0, z minus a will be 0, z minus a will be 0, so only a naught is the only thing left. So limit z goes to a, here f of z is a naught. So this name is removable singularity because the z equal to a is a singular point, and by applying this thing, limit z goes to a, your f of z is equal to a naught, then the singularity is removed. Okay. Hence I can write, hence by defining f of a, limit z goes to a, f of z means f of a. By defining f of a is equal to a naught, the function f of z becomes analytic at a. The function f of z becomes analytic at a. Becomes analytic at a. Become analytic at a. Okay. So if a is a removable singularity, then if I will define f of a equal to a naught by using this thing. So if I will define f of a equal to a naught, then then the singularity can be removed. Okay. So now go to next page. So uh, consider an example. Suppose my f of z, let my f of z is sin z divided by z. So what can I write? Clearly 0 is an isolated singularity because at z equal to 0, the function is not defined. So I can write clearly z equal to 0 is an isolated singularity. This is an isolated singularity. Okay. So since this is an isolated singularity, so how can I, if I will classify this as whether it is removable, pole, or essential, then it comes under which category? So I can write this is sin z by z, which is 1 by z whole into this is the expansion of sin z. This is z minus z cube by 3 factorial plus z to the power 5 by 5 factorial minus z to the power 7 by 7 factorial dot dot dot. So if I will multiply 1 by z, then this will be 1 minus z square by 3 factorial plus z to the power 4 by 5 factorial minus z to the power 6 by 7 factorial. Okay, plus dot dot dot. So there is no principal term because there is no negative powers of z or no negative powers of z minus 0. So we can say here the principal part of f of z, the principal part of f of z at z equal to 0 has no terms. Okay, so z equal to 0 is a removable singularity. So z equal to 0 is a removable singularity. So this is a removable singularity. Also, limit z goes to 0. What is your sin z by z? If I will take limit z goes to 0, this is your sin z by z. So sin z by z, this will be only 1 because here in place of z we will put 0. So this thing will be 1. So if I will define my f of 0 equal to 1, then the function becomes analytic at z equal to 0. So if we define f of 0 equal to 1, then the function becomes analytic at z equal to 0. Okay. So if I will say another example, so go to next page. Now consider another example. Let my f of z is equal to z minus sin z divided by z cube. So this will be 1 by z cube whole into this is z minus this is the expansion of sin z. We know the expansion of sin z. This is z minus uh, z cube by 3 factorial plus z to the power 5 by 5 factorial minus z to the power 7 by 7 factorial plus dot dot dot. So this will be 1 by z cube whole into if I minus my z, then what will left? This will be z cube by 3 factorial, then z to the power 5 by 5 factorial plus z to the power 7 by 7 factorial minus dot dot dot. So if I will multiply this 1 by z cube, then this will be 1 by 3 factorial, then this is z to the power 2 by 5 factorial plus z to the power 4 by 7 factorial minus dot dot dot. So here there is no principal term because there is no negative powers of z. So you can say z equal to 0 is a removable singularity. Is a removable singularity. And how the singularity is removed? So if we define my f of 0, because 0 is the singular point, so if I will define f of 0, this one 1 by 3 factorial, which is 1 by 6. So if we define f of 0 equal to 1 by 6, then the removable, then the unliticity is, then the singularity is removed. Or we can say if we define f of 0 equal to 1 by 6, then the function then the function becomes analytic at z is equal to 0. Okay. So now comes to the second definition. What is your pole? Now removal singularity is done. Now comes to poles. So what do I mean by poles? Let A be an isolated singularity of f of z. Let A be an isolated singularity. Let A be an isolated singularity for f of z. So if A be an isolated singularity for f of z, then the point A is said to be, then the point A is called a pole. Then the point A is called a pole if the principal part of f of z, if the principal part of f of z at z equal to a, at z equal to a has a finite number of terms, has a finite number of terms, has a finite number of terms. Okay. If the principal part of f of z, if the principal part of f of z is given by, if the principal part of f of z is given by f of z is equal to, sorry, only I will write the principal part where the negative powers of z minus a occurs. So if the principal part is given by b1 divided by z minus a plus b2 divided by z minus a square plus dot dot br divided by z minus a to the power r. So if the principal contains the element like this, where the last term, this br not equal to 0, then we say a is a pole of order r. Then we say a is a pole of order r, because this is the last term is, or this is the highest negative power is br divided by z minus a to the power r, and br is not equal to 0, this coefficient is not equal to 0, so the highest negative power of z minus a is r, so you can say a is a pole of order r. So this thing can be done by seeing the principal part of f of z. Okay, and you may note that a pole of order 1, a pole of order 1 is called a simple pole, is called a simple pole, and a pole of order 2, order 2 is a is called a double pole. So that is simple pole and it is double pole. So if we will see an example, suppose I will consider my f of z is e to the power z divided by z. So in its expansion, what I will get? This is 1 by z, and what is the expansion of e to the power z? This is 1 plus z by 1 factorial plus z square by 2 factorial, z cube by 3 factorial, like this. So if I multiply 1 by z, then this will be 1 by z plus 1 plus z by 2 factorial plus z square by 3 factorial, like this. So what is the negative power of z here? So this is the negative power of z. So I can say this is my principal part of f of z. So this is my principal part of f of z, and in the principal part this is only one term. So what can I say? What is the by seeing this function, you know, at z equal to 0 the function is not defined. So z equal to 0. Here you can say z equal to 0 is an isolated singular point. Is an isolated singular point, because at z equal to 0 the function is not defined, because it is e to the power z divided by z. So if the denominator will be 0, then the function is not defined. So z equal to 0 is an isolated singular point. And if in the expansion I am getting, this is the principal part. The principal part contain only this term. So what is the power of z here? Power of z is only 1. So you can say this is a simple pole, because order 1 is called simple pole. So here we can say, so z equal to 0 is a simple pole of aperture. Okay. So now comes to the next phase. So I will do another example. So suppose my f of z is, if my f of z is cos z divided by z square. Similarly, at z equal to 0 the function is not defined, so I can say here z equal to 0 is an isolated singular point. Is an isolated singular point. So if I will classify it in which category it is coming, then I will make the series expansion. Then what is the expansion of cos z? This is 1 minus z square by 2 factorial plus z4 by 4 factorial minus z6 by 6 factorial plus dot dot dot. If I multiply 1 by z square, then it is 1 by z square minus 1 by 2 factorial plus z square by 4 factorial plus z4 by 6 factorial plus dot dot. So what is the principal part? This is the part where the power of z is negative. So this is the principal part. This is the principal part. So what is the power here? Power is 2. So we can say this is z equal to 0. What is the isolated singularity? This is a power of 2 only. So I can say z equal to 0 is a double pole. Okay. So if it's order is 2, 3, 4 something, then I will say that is the pole of order 2, 3, 4 like this. But here the order is 2. So order 2 is named as this is double pole. So now comes to the third isolated singularity category, which is your essential singularity. Okay. So what is the definition of essential singularity? So what do I mean by essential singularity? Let A be an isolated singularity. Let A be an isolated singularity. Let A be an isolated singularity of f of z. Then the point A is called. Then the point A is called an essential singularity. Is called an essential singularity for f of z, or essential singularity of f of z, if the principal part, if the principal part of f of z, if the principal part of f of z at z is equal to a. at z is equal to a has an infinite number of turns. Has an infinite number of turns. Infinite number of turns. Infinite number of turns. So if the principal part of f of z at z equal to a has infinite number of terms, it is essential singularity. If it has finite number of terms, it is pole, and if it is the principal part has no term, then the singularity is removable singularity. Okay, by seeing the principal part of f of z, we are partitioning this thing. If it is principal part has no term, this is removable singularity. If it has finite number of terms, then it is pole, and if it has infinite number of terms, then it is a essential singularity. Okay, so now go to next page. So here I will see one example. So if I will take my f of z is e to the power 1 by z. So here clearly you can say since it is 1 by z is there, so z equal to 0 is an isolated singularity. This is an isolated singularity. So if we will classify it, then what is the expansion? This is 1 plus 1 by z plus 1 by z square by 2 factorial plus 1 by z cube by 3 factorial, like this. So what is the negative power subject, or what is the maximum negative power subject? See here, all the power subject are negative, and it is continue like this. So it has infinite. The principal part of f of z has infinite number of terms. Okay, here you can say here the principal part of f of z. Here the principal part of f of z has infinite number of terms. Has infinite number of terms. So what is the isolated singularity z equal to 0 is called an essential singularity. Is called an essential singularity. Okay. So if I will say another example, let the example 2 be suppose f of z is z square sine 1 by z. So clearly since it is sine 1 by z, so whatever the numerator will be, if the denominator is 0, then it is not defined. So you can say, so z is equal to 0 is an essential singularity. Sorry, this is an isolated singularity. This is an isolated singularity. So if again I will uh, I want to classify it, then I will add the expansion of sine 1 by z. This is your 1 by z minus 1 by z square by 2 factorial plus 1 by, sorry, this is cube, by 3 factorial, then 1 by z5 by 5 factorial, like this. So if I will multiply z square, then it will be, if I will multiply z square, then it will be z minus 1 by z 3 factorial plus 1 by z5, sorry, 1 by z cube, 1 by z cube 5 factorial, like this. So if the next term I will write, this will be 1 by z to the power 5 7 factorial. So like this. So similarly, if I will continue, then I will get more negative powers of z. So similarly here I can say here the principal part of f of z. Here the principal part of f of z has infinite number of terms. Has infinite number of terms. So z equal to 0, which is your isolated singularity, that is classified as essential singularity. So z equal to 0 is called an essential singularity. is called an essential singularity for f of z. Okay, so now classification of singularity is completed. Now comes to next page where I will show you what is the meromorphic function. So what is do you mean by meromorphic function? So what is the definition? A function f of z is said to be a meromorphic function. A function f of z is said to be a meromorphic function. Is said to be a meromorphic function if it is analytic except at a finite number of points. If it is analytic, if it is analytic, if it is analytic except at a if it is analytic except at a finite if it is analytic except at a finite number of points and this finite set of points are poles. And what are these finite number of points? And this finite set of points are poles. So except some poles, it is analytic everywhere. Then that function is called your meromorphic function. So if I give one example, now the first example will be suppose my f of z is 1, f of z is equal to 1 by z whole into z minus 1 whole square. So here z equal to 0 and z equal to 1. Here the function is not defined. So I can say here f of z is not analytic at z equal to 0 and z equal to 1. Okay. Also, so if it is analytic, this is not analytic, this is not sufficient also. Z equal to 0 and z equal to 1 are poles of order 1 and 2 respectively. Okay, these are poles of order 1 and 2 respectively. Hence, f of z is a meromorphic function. Because all the points where it is not analytic, these are poles, we get it. Okay, hence we can say your f of z is a meromorphic function. This is a meromorphic function. So if we will go to the next example, suppose if I consider a to the power z by z, then what is this one? This is 1 by z whole into 1 plus z by 1 factorial z square by 2 factorial. Similarly, z cube by 3 factorial plus dot dot dot. So if I multiply 1 by z, it will be 1 by z plus 1 plus z by 2 factorial plus z square by 3 factorial like this. So if I am writing this one, then where it is not analytic, this is not analytic at z equal to 0. Uh, this is not analytic. This is not analytic at z equal to 0 because this is e to the power z divided by z. So if the denominator will be 0, it is not defined, so z equal to 0. At z equal to 0, this is not analytic, or you can say z equal to 0 is an isolated singular point. This is an isolated singular point. This is also not sufficient. If I will say this isolated singular point comes under poles, then we can say this is a meromorphic function. So if I will distinguish this thing here, this is the principal part. Here z power is negative. Okay, so here z equal to 0 is a pole of order 1. So okay, this is a simple pole. So since this is coming under a simple pole category, or this is a pole, so we can say e to the power z divided by z is a meromorphic function. Okay, this is a meromorphic function. Okay, today only this much. Thank you.